Alright, silly people, here's the situation. Here's a more complicated circuit problem, one which involves capacitors as well as resistors with different resistance values. And we're still doing the same task of finding out what V1, V2, and V3 is using Kirchhoff's loop law and Ohm's law, and also the capacitor law, which is this guy. So the first part of the problem is to prove that the linear equations look like that for x1, x2, and x3, where the x's come from the fact that each of the voltages v1, x1, and e to the, those are all just pretty much the constants on the e to the I omega t stuff, which helps do with the derivative stuff. Okay, so I already solved this, right? If you watched yesterday's post, you may have already seen this. And so the setup for each of these equations that you're supposed to end up with is you take your voltage for whatever point you're on and subtract off all of the other voltages that are attached to it. So here's V1. You would subtract off V plus and divide V1 minus V plus by R1. Similarly, you would do V1 minus 0 over R4. And for the capacitor guys, instead of using Ohm's law, you use the capacitor law. So that is going to be the capacitance times the derivative of the first voltage minus the derivative of the second voltage, both with respect to time. So, and then you set that equal to 0. You do the derivatives. You just follow through the algebra. You cancel out all the exponents, and so you end up with this linear equation. V2 is much the same, except that there's two capacitors, but the setup is identical. You just take the first capacitor and the difference of the derivatives, and the second capacitor and the difference between those derivatives. Do the derivatives, cancel out the exponents, and group the answer together like this. Same thing with V3. It looks a lot like V1, right? The task of the problem is to figure out what each of the voltages are for these guys using NumPy linear algebra.solve. So we're going to start by setting up an input array, or actually we'll start by defining all of our physical variables. There are a bunch of them. Let me go ahead and import NumPy as np, and also we're going to need CMath for this one because reasons. R1, R3, and R5 are each 1 kilo ohm. I'm just going to define it like this. R underscore 1 is 1,000 ohms. And then copy that line down for 3, 4, or not 3, 4, but 3 and 5. So this and this, it's 5 and 3. R2, R4, and R6 are 2 kilo ohms. So R2 equals 2,000. And let me copy that down. Say bam, bam. R6 and R4 are also 2,000 ohms. C1 is 1 microfarad, or 1e minus 6 farads. And C2 is 0.5 microfarads, or 0.5 e minus 6 farads. X plus is 3 volts. Omega is 1,000 seconds, or 1,000 inverse seconds. With that, we can set up our input array, which we're still going to call A. It's going to be a NumPy array that is going to be huge. It's going to have the float data type, and it's going to have 3 rows. So let me do row here and a row here. And then space these commas forward so that I can be a sane person. The first element of the first row is going to be the constant that's attached to x1 in the first equation, and that is 1 over r1 plus 1 over r4 plus 1j, j being the Python equivalent of I, times omega. I better capitalize this R here. I really love that pop-up. That reminds me what an array is every time I'm mousing over an array. And then, let's see, yeah, that's the first component. The second element of the first row is the stuff that's multiplying x2 in the first equation, so minus 1j times omega times c1. And then the last element of the first row is 0 because x3 is not in this equation, right? Next row, so we're looking at this equation now. So x1 has minus I omega c1 on it, so minus 1j times omega times c1 on there. And I just realized that this should really have a c1 on here. c1. Glad I caught that just now. And then I'm going to put a comma here, and I'm going to space the comma forward so that it's lined up with the other first element of the first row. And then the second component of the first row, or second row, so the diagonal element is 1 over R3, or whoops, 1 over R3 plus 1 over R6 plus I, or not I, but 1j times omega times C2. That's it, I think. Actually, I was looking at the wrong equation. My bad. It should be 2 and 5 for the r's, and then that is C1 here, but then also plus 1j times omega times C2. Yeah, that's a really long element, and I'm going to space this element forward to line up with that one. And then the third element of the second row is going to be, what is it? It's this guy here, minus I omega times C2. So pretty easy, minus 1j times omega times C2. All right, and I'll space this 0 forward so we're all lined up again. All right, third row, first element is 0. Nice. Space that 0 forward so everything is simpatico. Second element is just minus I omega times C2, so minus 1j times omega times C2. So just space that forward a bunch so we're lined up there. I really love that pop-up. Can't get enough of it. Right? I don't like that space between the minus sign and the 1. Then the third element here is going to be just 1 over R3 plus 1 over R6 plus I times omega times C2. So we're doing 1 over R3 plus 1 over R6. And I should better capitalize that R. And then it's plus I, or 1j times omega times C2. And I realize now that if I had spaced any further forward, it probably would be behind my face. But I think it worked out. Oh no, it looks awful. Let me just make a few lines so we can see everything. But that's the input matrix. I think I did that right. Put all the omegas and the r's where they need to go. The next bit is to do the input vector that you put into the solve function. So that's going to be v equals numpy array of floats, and then the elements of it just end up being, let's see, x plus over r1, x plus over r2, and x plus over r3. Lovely. So x plus over r1, comma, x plus over r2, comma, x plus over r3. Okay, so that's cool. Now we can just have x be equal to the numpy.linalv.solve function, and you can just put in the arguments a and v, and it will return a bunch of solutions for x1, x2, and x3, if I did that correctly. And I just realized that this array should probably be a complex one, not a float one. But yeah, look at those x1, x2, x3 values. Notice they're complex. And so that's why the next bit of the problem is to actually have it, or it's not here, but it was on the next page after this one, actually print out what the voltages are on those. And x1, x2, and x3 effectively represent the magnitude of the voltage and also the phase of that voltage. So what we can do is we can run a for loop for I in range 3 to print out each of the voltages using cmath.polar of x indexed I, which it's a thing which is going to return a magnitude, which I'm going to call R, and a phase, which I'm just going to call theta. So yeah, once you have that, you can put your print line. I'm going to be fancy with my print line and say v subscript, and then put a plus here. And the subscript is going to be I plus 1, right? And then comma, we're going to do an equal sign, and then another comma, put R here, and then put another comma here, say volts, space, semicolon, and then you can get into printing out the phase. That will be equal to theta times 180 divided by pi to convert it into degrees from radians, and then put the word degrees here for units. And when we print it, you cannot concatenate string not int to string. Oh yeah, that's because you need to put a string around these parentheses, and now it will look all pretty. So yeah, neat problem.